4.2 Quadratic Relations. A quadratic relation is a relation whose equation is in the form y equals ax squared plus bx plus c. This is known as the standard form of a quadratic relation. Now, a standard form of a quadratic relation, notice, has no brackets, and the standard form has the same letters that you saw when you saw the standard form of a line. Now, the standard form of an equation of a quadratic, it has the following conditions. A, B, and C are a specific type of numbers. These numbers now belong to, so this is what this symbol means here, belongs to. Okay, so it looks like you saw there, a C with a line in the middle, or a rounded E. This means that A, B, and C belongs to, it's a part of an element of. It is part of a world of numbers called real numbers. Now watch how we draw this symbol real. We put two bars, and then we make an R with the first bar. So again, just watching that, you write, here we go, one bar, a second bar, and we make an R with the first bar. That means that these are numbers that belong to real. And specifically, A will not equal 0. So that's going to be important that we're going to add on to this. Now again, this symbol means belongs to, and this means real numbers. Okay, so again, note here, A cannot equal 0. What are real numbers? Well, let's start with our idea of how we began to count in math. When we were first born, we were taught in the world of natural numbers. So we naturally begin counting on our fingers, 1, 2, 3, 4, 5, 6, and so on. Our parents counted our fingers and our toes when we were first born. Now the natural number world got expanded. It expanded into a new world called whole numbers. What is the difference between natural and whole? Well, whole numbers start with a whole. Yes, folks, it starts with the number 0. So whole numbers is one addition from natural numbers. So it has its own little world. Then our whole world got expanded to include the next world. That world we were exposed to, if you were born in the winter time, you were exposed to this very early in life, and that is integers. Now notice how we drew integers, just so that you can focus on that, folks. You'd think that it would be the letter I, because natural starts with N, whole begins with W. Well, how do we do the world of integers? Well, we can't use I because it has another world. I involves another world, so we use a slanted I. So it looks like a Z. And again, the double bar is in the middle, so the I has now been slanted to create our Z. So what are we looking at? Natural numbers, whole numbers, and now integers. What goes beyond integers? Well, you were introduced to this world pretty early, but you didn't know what that world meant, and that was the world of rational numbers. So this represents Q for quotient. There's a bar to indicate it's a world of numbers. This is the world of integers. Integers have, sorry, not integers, quotients or rational numbers, i.e. fractions. Okay, fractions contain integers. Integers contain whole numbers. Whole numbers contain natural numbers. So our world is now expanded to include all possible rational numbers. Anything that can be expressed as a fraction. Well, there's another world way over here. In fact, this world is actually bigger than this whole entire world. But for the sake of just drawing here, we'll just draw it small, because it only is one letter, and that is the world of irrational numbers. Irrational numbers are numbers that don't fit into these categories. So, it cannot be expressed as a fraction, ultimately. What number cannot be expressed as a fraction? Hopefully you're thinking, oh yeah, pi, root 2, root 3. Those are all irrational numbers that will, okay, sorry folks, let's just change the colors on this. So, irrational numbers are all numbers that do not fit in this world. Well, how do we combine all of this world with this world to put it into one giant world. And that world, folks, is real. That is the world of real numbers. The world of real numbers means I can plot them on a graph. Pi is equal to 3.14 and so on. I can plot a decimal value close to pi. I can plot any of the numbers in real onto a graph, and that's why it's called real. Those of you wondering, is there an extension beyond this? Yes, we can plot even imaginary numbers. Yes, there is such a thing as imaginary, but we don't deal with that here. So let's move on. Real numbers it is. That's what we're working on, folks, and that's what we want to see. All right. Now, a parabola is the graph of a quadratic relation. Now, it is a U-shaped curve that represents a parabola, a graph of a quadratic relation. The direction of opening of a parabola has some important features that we have to remember. For example, if the a value is positive, the parabola opens up. So again, we're looking at the standard equation of a parabola. Here it is. We're looking at the a value. If the a value is positive, that means greater than 0 is a positive number, any positive number, you're guaranteed that the parabola opens up. Next, if you have a value less than 0, you're guaranteeing that the parabola opens down. So greater than 0, it opens up. Less than 0, it opens down. So a negative number opens down. Now, there's another form. If we see this form, this is called the vertex form of a parabola. The vertex form tells us something important about the parabola. It tells us something called the maximum or minimum, also known as the optimum value. The optimum value is either maximum or minimum, which indicates the highest or lowest point on the graph, the y value. In the case of our vertex form, the k value indicates the highest or lowest y value on the graph. That's the k, that's the number over here. What else does this form tell us? Well, it tells us the axis of symmetry. An axis of symmetry is an imaginary vertical line that passes through the vertex. And that equation is x equals h. It has the equation x minus h equals 0, so we can set the bracket equal to 0, because that's what you're essentially doing. So that means x equals h. That's what I was talking about earlier. Something else to note before I forget, on the basic form up here, I kind of put it as a side up here, folks. The reason it's a side is that it's not really a critical part of this standard form, but it is a piece to remember, is that the c value in standard form represents the y-intercept. Okay, so the c value is the y-intercept. That's only if it's in standard form. It's not so important, so I don't even put that in part of the definition. Definitely, the a value plays a major factor because whether it's a in the first form, a in the second form, or a in the last form, it means the same thing. If a is positive, it opens up. If a is negative, it opens down. That is the same whether we look at it in standard, vertex, or factored form. And this is the last one. This one is called factored form. Factored form involves identifying one crucial important part of the parabola. Not every parabola has this, but definitely it's an important crucial part. And that is known as the x-intercepts, zeros, roots, and finally factors. And we don't really use this word as much, but this is known as the factored form of the parabola. Now, what these are, x-intercepts, zeros, roots, and factors, is the x-coordinates of the points where the graph crosses the x-axis. And you guys should know this from grade 9. X-intercept means where does it cross the x-axis. Another word is zeros, another word is roots, and factors. But I want you to note which values tell you the x-intercepts. This would be the value of r and the value of s. roots starts with R and ends with S. So you have the R and the S here. You notice that intercepts has the R and a S. Zeros has an R and a S. Factors has an R and a S. So ideally here, it's the R and S represents the roots. Now, what other pieces do we need to know? Well, x equals R, or x, sorry, let's try that again. We set the bracket equal to 0. That means this is a 0 and this is a 0. So we set each bracket equal to 0. What does that mean? X is equal to? Well, x is equal to R and x is equal to S. Note that inside the bracket it says minus R, but when we pull it outside of the bracket it becomes positive R. And that was true for the last example as well, folks. Because if we just look at the last example, remember about x equals h, look inside the bracket, it says minus h. Looking outside, it's plus h. So again, that all has to do with the fact that they're inside brackets. Think of the brackets as a sort of, let's say, cloud. It clouds up the idea in here. Once we pull it out, it becomes a value that we're used to. Okay, next part. Here's a graph. Let's talk about all the different parts of this graph. First of all, I know this graph opens up. The arrows are pointing upwards. This graph opens up, so our A value should be positive. Down here at the bottom, this is our vertex. Okay, so we've got a lot of things going on this page, so we're just going to take our time and go through this slowly. Ready? So, first of all, we have this point at the bottom. Down here, this is known as the HK. The coordinates of this would be HK. Wherever the parabola turns, the turning point is the vertex. So we have our vertex. Something else, this particular vertex shares two specific pieces of information. Not only is it the vertex, but it is also the y-intercept. Okay? Not only is it the y-intercept here, not always, folks, keep that in mind. Something that it always is it's either a max or a min. In our case, it is a minimum. The y value is the minimum value. All right? Then there's this thing. This thing coming down is known as the axis of symmetry. It divides the parabola into two pieces. X equals h is our axis of symmetry. And again, our vertex shares two pieces. It shares the y-intercept and the vertex, so it's two pieces. Axis of symmetry is x equals h. It's a minimum value. The minimum value is whatever number this is. How low does it go implies minimum value. So we have all of these pieces that play an important part in our graph. Next part, looking at these pieces. What are these? Well, these folks are mirror images of each other. You can see across the the axis of symmetry. So this particular line, x equals h. We can see that each point has a mirror image across the axis of symmetry, because that's what the axis of symmetry is. It is a mirror. It is a line that represents a mirror, where it divides a parabola into two equal halves. So each of these points is a mirror image of each other. These are also known as our roots, zeros, x-intercepts, and even factors, if you want to call it that. Alright, well, that's the end of this video with respect to, again, we're talking about the parabola and introducing the different aspects. You'll have to go on to part 2 of the video to see a little bit more details as far as 4.2 is concerned. Alright, folks, have a numerical day. Take care.